I want to talk about things growing out of the golden ratio. And probably a lot of people here love the golden ratio, but there are many people who feel that they're a bit fed up with it turning up all over the place. Probably there are many people here who've taken the next level and have got fed up with people debunking the golden ratio. So maybe it's time to go back to it and do some mathematics with it and say, what are the interesting properties of the golden ratio and what other numbers and systems can we find which share those properties? And so I want to look at two properties of the golden ratio. Firstly, that it's the ratio between the edge and the diagonal of a pentagon. And secondly, that it can be put into this rectangle where you have the rectangle, you cut off a square, and you get a similar rectangle. And we can construct the value of the golden ratio from here. We can move numbers around, find the formula, and solve that to get the value. And so going back to the pentagon, we can look, instead of looking at the pentagon, start looking at regular polygons. For example, with the octagon, the edge to the diagonal has this property, and it's the 1 plus the square root of 2. For the heptagon, we're now up to cubic numbers, and so we can't give nice written radical forms. So I'll just leave the polynomials up. But you can find a polynomial system that gives you the length of the edge to the diagonal for the heptagon, or for the nonagon. And in fact, you can generalize this and find interesting scaling systems for any n-gon, and that's something that's been reasonably well explored. There are a few papers out there. So the other way is to go back to that rectangle, and we can do a similar thing to any rectangle. So I start with a rectangle. This is no longer a golden rectangle. We can cut off a square. We can cut off squares of what's left over. We can cut off more squares, and we might end up with nothing left. And this construction is exactly the continued fraction algorithm. And so you can do it to any rectangle. And of course, in this case, the rectangle terminates. And if you have a rational proportion between the height and the width, the system will always stop. Slightly more interesting, like the golden ratio, what could also happen is we keep doing this, and at some point, the rectangle we end up with is similar to either the rectangle we started with or another rectangle we've already seen. And once you get that, you can tell that you're going to go into a periodic loop, and there's this old result of Lagrange, one of the many results called Lagrange's theorem, which says that you will get into that loop if and only if you have the solution of a quadratic equation. So let's consider another rectangle. And this time, instead of cutting off a square, I'm going to cut off a similar rectangle. I'm then going to cut off a square, and so I'm left with a similar rectangle. I can play the game of doing some algebra and get the solution. And this x cubed is equal to x plus 1, slightly familiar. So we have a very interesting proportion system that really turns up in many places. There's an interesting three-dimensional construction you can do with the proportion. And when you have a proportion system you like, of course, you make a set of dividers. And you go out and you say, can we find this appearing in places? So here are some places. But this set of dividers just mathematically does have a really nice property. If you look at this, the distance between any two prongs of the divider is a power of the same ratio. And this is the largest set of dividers that has that property. And so you can then use this proportion system to start making images, and I think it has some interesting properties. But we've also now got a system we can use to generate whole families of numbers. We can just say, take a rectangle and cut it up into similar rectangles and squares. So if we allow ourselves 2, we get these 3 different numbers. 2, good proportion, which I talked about last time, the golden ratio, and the square root of 2. If you go up to 3 blocks, you get some more. Remove the numbers we've already seen from this, and you have 11 different proportion systems. We'll also get rid of the rational ones, which leaves us with these proportions. And they're all quite nice. We have a variety of simple quadratics. We have the square root of the golden ratio. We have a couple of simple cubics. And then we have one which looks a bit more complicated. But this one should be familiar to you. You've seen this before. So these rectangles somehow give us the proportions of the heptagon back. And we can do the same thing for the nonagon, which needs these 4 points. So simple numbers in these 2 different systems seem to be the same. You can make some mathematical conjectures on this, which I don't quite have time for. And I can't go beyond the nonagon, so do we need a new system to get to cortex? And I'd love to hear anyone who's seen this sort of system or explored it before. I've found a few references to it, but any exploration of similar systems from this, I'd be fascinated and very interested in hearing about it. Thank you very much.